In today's video, we will learn how to load and work with the awesome Mixtral 8X7B model on a free T4 GPU in Google Colab. Now this model is a mixture of 8 different 7 billion parameter models, and this means it's a huge model, something that would ideally require a huge GPU. But we will use quantization and some clever use of parameter offloading to load it and run it on a regular, freely available T4 GPU. Now I highly recommend watching my LLM concepts playlist because it covers important concepts like quantization and parameter offloading that we will be using in today's video. Alright, so let me take you through the code. Please note that this code is already available on my GitHub, and I'll also be leaving a link to this Google Colab notebook in the description of this video. So we start by importing NumPy, which is used for numerical calculations. In this line, we're importing clear output because we're using it in the last line of this cell to remove the output of the cell for declutter. These few lines set the environment variables and library paths for the NVIDIA GPU. In this line, we clone the repo we want to use from GitHub, which has the code that will help us run Mixtral with parameter offloading. So we'll be able to run it on just a T4 GPU. In this line, we cd into the cloned repository, and then we use pip install to install all the requirements and the dependencies from our requirements.txt file that we'll find in this repository. This line imports the sys module, which provides access to variables used by the Python interpreter and to functions that interact strongly with the interpreter. Using sys, we append a directory called Mixtral offloading. Then we import the PyTorch library, which is widely used for machine learning tasks, especially for deep learning. This line imports the functional module from torch.nn and aliases it as f. The module essentially provides functions that operate on neural network layers and tensors. Here we are importing the base quantize config, which will help with quantization. Then we import the snapshot download library from Hugging Face Hub, which will help with downloading the model snapshots. We again import clear output because we'd want to clear the output of this particular notebook's cell. This library will help us create progress bars and is used quite often in Colab, especially when you have to load the models. These classes are part of the Hugging Face Transformers library and are used for loading model configurations and tokenizers automatically. This is used to manage the logging settings. These are custom configuration classes used for configuring the model's offloading and quantization settings. The Hugging Face library also comes with a progress bar, and this is what we will disable to avoid cluttering the output windows. Now this entire section is about initializing the model. So we start with mentioning the model names to be used for the model name and the quantized model name. The config variable holds the configs of the quantized model, and the state path variable will have the path to the downloaded quantized model. Then we set the device on which the model will run. In this case, it's set to GPU. Here we mention how many layers are offloaded to the CPU to reduce load on the GPU. So you'd ideally want to increase this number if you have a smaller GPU. This section specifies how much of the computation will be offloaded and how much will remain on the GPU. So we've used fields like main size, offload size, buffer size, and offload per layer to define the specific values. This defines the config for the attention layers and specifies the number of bits for quantization, group size, whether to quantize to 0 or scale the quantization. And this section similarly defines the config for the feedforward layer. And in this section, you'll see that the model variable is being assigned some value, and this is the model variable that we'll be using in the very next cell to run the model. And what's happening here is that this variable is assigned the result of the build model function, which constructs the model using the specified device, the quantization configuration, the offloading configuration, and the state path. It also loads the model's weights and sets up the necessary components for inference. Now the next section is all about running the model. So here, as you can see, from Transformers, we import text streamer, which is a part of the Transformers library. It helps with streaming the response little by little, instead of generating the entire response in one go. Streamer also helps with efficient memory usage. Then we have our tokenizer. So tokenization is the process of breaking up the prompt and response into individual words for ease of processing. So each type of model like BERT and GPT, etc., follow a different strategy for tokenization. Now this is why we use something called as the auto tokenizer, which we have imported earlier in one of the previous sections. And we use this because the auto tokenizer helps us manage the tokenization for different sorts of models. So for example, BERT, GPT, we don't have to worry about it. Auto tokenizer takes care of that for us. In this line, we pass the tokenizer to text streamer. We set the skip prompt to true to ensure that the text generated by the LLM won't have the prompt text. And here we have set the value of skip special tokens to true. And what this means is that the text will not have any special tokens like A or EOS, which stands for end of sequence, etc. Now these above three values are initializing our model. Past key values stores the state of the model, so we want to set it to none since no text generation has occurred previously, and this is the right thing to do. We would ideally store the generated text sequence, and since nothing has been generated yet, it will be none right now. The sequence length helps keep a track of the input sequence, and since nothing has been yet started, it'll be 0. So we start an infinite loop and run till we find a break. Then we prompt the user to enter the text. And we store the user's input in this variable, which is user input. We create a dictionary for the user's input with role user and content as user input, which we have just accepted from the user. This line tokenizes the user's input using the tokenizer and converts it into input tensors. Apply chat template formats the user's input according to a specific format. And return tensors is equal to PT indicates that output should be PyTorch sensors. In this sentence, we're checking if the past key values is none. Now we had set the value for past key values just a few lines above. And what this specifies is that this is in fact the first time we're interacting with the model. Now if it is in fact the first interaction, this line creates an attention mask tensor with the same shape as the input IDs tensor, filled with ones. This ensures that the model pays attention to all input tokens. If it's not the first interaction, then this code will get executed. This line calculates the sequence length. It sums up the length of the current input IDs and the length of the past key values from the previous iteration. And it's used to determine the length of the attention mask for the current input sequence. This line creates an attention mask tensor with shape 1, sequence length minus 1, where sequence length minus 1 is the length of the current sequence. This mask is used to ensure that the model only attends to relevant tokens in the input sequence. This line prints the word Mixtral without a new line character at the end, meaning whatever is printed next will appear on the same line. We now attempt to generate some text with the initialized model. So we used model.generate function. We pass input IDs and attention mask defined above. And as we know, past key values are key pair values from a previous text generation. Temperature helps us control the randomness of the output. Closer to 2 means it's more random, and closer to 0 means it's more deterministic. Top peak controls nucleus sampling, ensuring that the cumulative probability mass of the generated tokens doesn't exceed this value. We define the total number of tokens to be used with max new tokens. Pad token specifies the token ID to be used for padding. Tokenizer.eos token ID refers to the end of sequence token ID in the tokenizer used by the model. Return dict in generate is equal to true indicates that the function should return a dictionary containing the generated sequences and other relevant information. Output hidden states is equal to true specifies that the model should also return hidden states in addition to the generated sequences. And this line extracts the generated sequences from the dictionary result and assigns it to the variable sequence. And finally, this line updates the past key values variable with the latest key value states obtained from the generation process, likely to be used for subsequent generations. So here at the end of the file, we can see the output being generated by this model, where the user is being asked for a prompt and he says, write a funny poem about Python, please. Mixtral returns back a complete poem, and the user continues to have a complete conversation about the generated output, and Mixtral is able to carry forward that conversation multiple times over. And that's what shows the versatility and the awesomeness of this model. Thank you so much for watching, guys, and I'll see you in the next video. I hope you've watched the other playlist as well, which is the Gen AI and LLM projects playlist. Make sure you share this with your friends and you like and subscribe to this channel, because this is all awesome free content, and I think you should share it with as many people as possible. Thank you, and I'll see you in the next video.